today. So hopefully this echo will improve as we go along. So do you guys still hear an echo at all?
No, we're good.
Okay. Let's continue on with this. Okay. So welcome. So this is our the Wednesday lecture of week 9 of EGME 417. So we're going fully virtual now. So as you can see from the background behind me, I'm in my office right now, and I'm not in the classroom anymore. So the we're going to continue on like this because due to the the email from the president sent earlier today, he basically officially said that we're going to continue virtually until the rest of the semester. So that includes the second midterm exam, and we don't have a final exam here, so that doesn't affect us. But we're going to be like this. So it's that's kind of the situation that we have right now. So the plan for today is to continue where we left off on Monday, talking about the finite volume method. So we'll finish the introduction notes, and then after that, we're going to start working on the diffusion. Okay. Question.
So if we are going to be fully virtual, how are we going to do it? Like midterm 2, is there just going to be like a time effect where you open up the midterm, we have a certain amount of time before we turn it in, or?
Yeah, so that's what I'm thinking right now. So I think the second midterm is going to be a take-home exam, just because it's it's not going to be feasible for you guys to come to campus at all, because all the classrooms are locked, and it's not good right now. I mean, that's the whole point of the quarantine, is to prevent everyone from kind of gathering in one place, because that's kind of how the virus is going to spread. So there will be no, at least for this class, there's going to be no further need for you guys to come to campus. So probably for the second midterm, I'm going to work on a take-home final where I'll probably open it up for 24 hours, and you'll have that amount of time to do it. Yeah, so that's the plan right now. Okay. Any other questions before we get started for today? Okay, so if you're just joining us right now, so I'm in my office right now, so I have my headphones in, so I can hear you guys if you turn on your mics. So if you have questions at all during the lecture today, you can, of course, still use the chat. So I have the chat that's right in front of me right now. Or if you want to just speak, just say a question, just turn on your mic, and I'm happy to answer that too. Okay. Actually, before we begin, there's one more order of business that we need to take care of. So I know that since the campus is basically totally closed down now, there's no way for you guys to access the computer labs here on campus. So that means that any MATLAB work that we're going to be doing for the rest of this semester, that you're going to have to do it on your home computer. So I know not everyone has a computer that can run MATLAB that well. So we do have an option for you. So our IT department's been working really hard this week, and they've set up what's called a virtual machine, which can be used for you guys to basically run engineering programs outside. Okay. So for us, I'm not sure how many people are unable to run MATLAB, but it's if you're unaware, you can obtain it free from the student store. So if you want, I can put information on about that online. But if that's not an option for you, if your computer is unable to run MATLAB, then I can post. So I put together a PDF document for telling you guys how to use the virtual machines to run MATLAB. So I put that together mostly for my 410 class, which they have to use ANSYS, which is a finite element program, but you can use MATLAB through this thing too. So if you are unable to access MATLAB from your personal computer, then that can be an option for you. I'll have to warn you though that the virtual machine is really slow. So if you can run MATLAB on your own machine, that's going to be much better than trying to run it on the virtual machine, where it's not that great an option. That also, and that there's very limited space on the virtual machine, so only a few students can use it at the same time. So if you can use MATLAB on your own machine, that's usually going to be preferred. Right? So we have one more question. So the question is there going to be class next week on Monday? So since the original plan was to have the early next week to be non-instructional days, that's the Monday and the Tuesday. So I'm going to honor that. So Monday we're not going to have any lectures. So we'll take the day off. and I'll use that to kind of prepare and kind of fine tune this this virtual lecture so that we'll be good to go for the rest of the semester. But we will have lecture next Wednesday. Okay. So just to kind of confirm it, after the lecture today, I'll send an announcement through Titanium, just reminding everyone that that Monday there's not going to be any lecture at all. Okay. Has anyone had a chance to look at the YouTube lecture from Monday? I checked it out myself a little bit, but I didn't watch it kind of end to end because it's for me it's really difficult to hear me talk on a video like that. So I didn't get a chance to watch the whole thing, but it seems like it uploaded okay and was able to crop okay. But did anyone experience any difficulties watching that lecture on Monday? Okay, so the plan is I'm going to do the same thing for today. So right now the Zoom is recording. So after the lecture, basically Zoom will send me the video file and I can throw it up on YouTube for you guys to view later on. Okay, so if there's no more questions, let's go ahead and get started. So I have a new setup today. So today I have both my computer, and I also have my iPad here, so I can kind of write stuff in real time as we're doing the lecture, because I think that's a little bit nicer than just highlighting stuff. And my handwriting is a little bit better than trying to write with the mouse. Okay. So let's go ahead and get started. So hopefully you have you can see my lecture notes here. So let me go to the whiteboard. Okay. So is everyone able to see kind of a blank screen on the second instance of of me joining the Zoom meeting? Great.
Yes.
Okay, so let's recap what we did from last time. Okay. I'm on eraser mode. Okay. Okay. So last time what we did was we started going over the idea of finite volume analysis, finite volume methods. Okay. So we didn't really get to it in the end, but we kind of introduced some tools that we're going to need to do, because the big difference between finite volumes and finite differences is that we're going to be performing a lot more integrals. Okay? So we went over two kind of big integration kind of techniques or schemes, I guess you can say, that we're going to use. So the first of which is called the divergence theorem. So the divergence theorem, we didn't go through the proof of this, but I just wanted to give you guys the upshot. Where the divergence theorem, what it allows us to do is it allows us to convert one integration to another type. Okay, so in particular, we learned how they can convert region integrals to boundary integrals. Okay. So the example that I gave you guys in 2D. Okay. So in 2 dimensions, let's say we have a double integral. Okay. We take the double integral of the divergence of some vector u. Okay. Where this quantity right here, this is the divergence, right? So divergence is defined by the nabla operator, dot product with u. Okay. Okay. And then through the divergence theorem, what we say is that this is equal to a line integral of u dot product with n ds. Okay. So just like the definition, this right here, this is our boundary integral. Right. And then this quantity right here, this is our region integral. Okay. So schematically, it looks something like this. So say that we have a rectangle like that. Okay. On the left-hand side right here, what we'll be integrating, we're integrating over dA. So this would be this entire area, just like that. Okay. But then if we compare that to a boundary integral, you can see that we're integrating over a line. So what we're doing is we're integrating over the boundary of this guy, just like that. Okay. And so that's going to help us out a lot once we're defining our finite volume method, because a lot of the terms, especially the diffusive term and the convection term, we want to evaluate it on the boundary, just like this guy. Okay. Okay. So that was the divergence theorem. So that was the first one that we'll do. So we'll see that in action today. Okay. So any questions on that before I clear the board? Okay, so let me clear this. Okay, so the other thing that we went over last time was called the trapezoidal rule. Okay, so the trapezoidal rule, it was kind of like what we talked about. It was a Riemann sum. Okay. Oh, we have a question. So the question is, does the unit vector matter? And the answer is yes. So I'll kind of save that for when we actually start solving diffusion problems, but we'll see that when we take the dot product of the vector with the normal vector, that's actually going to help us evaluate that integral. But I think it'll make more sense once we get to the diffusion term. Okay. Yeah, great question. Okay, trapezoidal rule. So trapezoidal rule, what this allowed us to do was to evaluate integrals without actually integrating. Right? Okay. Because what we can say is that if we want to evaluate an integral, one way that we can do it is we can take the integrand and then just evaluate it at the centroid. Okay? So we saw this in action in 1D. So let's say that we have some integral of some function x dx, okay? And we're going to integrate it from a to b. What we say is that one way that we can evaluate this integral is we just take f of xc, where xc, this is the centroid of the domain. Right. Where xc, in this case, would be b plus a divided by 2. Okay. And then we multiplied it by the length of the domain. Okay. Where li is equal to b minus a. Okay. So we saw an example of this in action on Monday. So we saw that it can work for that, and then we'll see we're going to use this in 2 dimensions too, and we'll kind of see that as we get to diffusion in 2D. Okay. Okay. So today the plan is to kind of put these guys together and to actually kind of formulate what the finite volume method is. Okay. So any questions on this before we move on? This is all just review from Monday.
Where
Okay.
did the B and the A come from again? Are those just like our limits?
Yeah, so the B and the A are just the limits of integration.
And then so you have xc is equal to B plus A divided by 2?
Xc is equal to B plus A divided by 2.
Thank you.
Okay. Okay, the finite volume method. Okay. So the finite volume method, remember what we're doing is we're taking our general conservation equation. Okay, so this is FVM. Right. Okay, so let's take our general conservation equation, but let's take it in the steady form. Right. Right, so in the steady form, and then if we take it in vector notation, it looks something like this. Okay. Okay. So I'm taking it in 2 dimensions right now, right? So that's why we have q of x and y, right? Oops. Okay. So let's label some of these quantities here, right? So v right here, this is our convection velocity. Right? So k right here, this is our diffusion coefficient. Okay. And then q right here, this is our source term as usual. Okay. Right. So to apply the finite volume method, we're going to take this equation, and what we're going to do is we're going to integrate it. Okay. Because remember, what's different about the finite volume method is that instead of worrying about the grid points in our in our mesh, what we're doing instead is we're worried about the regions. Okay. It takes forever to erase like this. Okay. So what we're going to do is we're going to take this equation and we're going to integrate it over the region of a cell. Okay. So let's take these equations and let's do that. Right. So since we're working in 2 dimensions right now, let's do a double integral over each of the different terms. Right. So first, let's do the convection term. So the convection term, we have double integral of our convection. Okay. And then it's going to be equal to double integral of our diffusive term. Okay. And then to this, we're going to add the double integral of our source. Okay. Or remember the region in which we're doing this is going to be the region over the cell. Okay. So if we take our general kind of a domain like this, okay. So let's say that we have some kind of general 2-dimensional domain like this. So when I say we're going to integrate over a cell, what I mean is that we're going to take just an individual cell, say this one right here, right, and then going to integrate it over this area. Okay. So we're going to do one cell at a time. So what the finite volume method says is that we're going to take the integral of our equation over each of the different cells, and we're going to do that for every single cell, and then from that we're going to get an algebraic equation. Okay. Because remember, even though we're performing this integration, the end goal here is going to be the same. So the goal is going to be to use this integration equation to get an algebraic equation.
Professor, the region of the cell is just dA.
Yeah, so dA, that's the area of the cell. That's what I mean by that.
Thank you.
Yeah. Mm-hmm. Any other questions before we move on? All right, so I think the eraser on this whiteboard is not that effective, so I'm just going to clear the board kind of every time. So, but before I clear, I want to make sure that everyone kind of has a chance to write stuff down. Okay. Okay, so let's go ahead and clear this. Okay. So if we look at the integrations that we just did, we should notice that 2 of them we can actually apply the divergence theorem to. Okay? So in particular, the integrations that we can do that for the convection integral and the diffusion integral. Okay? So let's apply divergence theorem to convection and diffusion integrals. So let's do each of them kind of individually. So first, let's do the convection one. So for the convection integral, we have double integral of nabla dot p v dA. Okay. So if we use the divergence theorem, we can convert this guy into a line integral on the surface. Okay. So that's going to be equal to line integral of phi v dot n dA. Okay. So this is the convection integral. Okay. And then now let's do the same for the diffusion integral. Right? So for the diffusion integral, we have double integral of nabla dot k gradient of phi dA, right? And then through the divergence theorem, this is equal to line integral of k delta phi, just like that, dot n hat, okay, ds. Oh, sorry, this one, this integration should be ds right here because it's over d. Okay. Okay. So let's label this. This is the diffusion integral. So there's a reason why we can apply the same divergence theorem for both of these integrals. So even though they both kind of represent two different physical phenomenon, they both kind of do the same thing. Okay. So both of these integrals, what they're often called the flux integrals. And so the term flux, what that means is that it's that's another word for transport. Okay, it's kind of a fancy word for it. Okay, because if you remember what convection and diffusion represent, so the convection and diffusion represent different ways for our quantity phi to be transported in our domain. Okay, so both of these integrals kind of represent that fact. Okay. So in particular, when we use the divergence like this, what we say is that our phi. Okay,
Professor, is that I'm sorry, is that vector arrow over the phi and del?
Yes. Yeah, great question. Actually, so this quantity right here, remember this is the gradient, right? So our phi itself is a scalar, right? But when we take the gradient of it, that turns it into a vector. Because let me write that down here. So when we take the gradient of phi, because remember we're in 2 dimensions, what this turns it into is a vector, where each of the components of the vector are partial derivatives of phi in each of the different directions. Okay, so the x component of this is going to be d phi dx, and then the y component is going to be d phi dy, right? So this is going to be important later once we dot product that with our normal vector, kind of like what was alluded to earlier, but we'll see there. But yeah, great question. I always kind of forget this because I go over this in some of my other classes, but sometimes I kind of forget in some other classes. So it's kind of good to kind of establish that. Okay, let me erase this guy. Okay, so our phi in this case can be anything. So remember, because this class is called computational heat transfer, so the phi can sometimes be temperature. Right, where temperature represents energy. Another thing that our phi can represent is also mass, right? Okay. So essentially what we're saying in our general conservation equation is that temperature or mass can be transported by convection or diffusion. Okay? And in particular, once we apply that to a volume like this, or like a cell, well, we say that phi can either enter or leave our cell by convection or diffusion. So it's kind of like a conceptual kind of understanding about why we use divergence theorem on these, because because both of them represent transport, it makes sense to kind of evaluate these guys at the boundaries, because if we know how much of phi is crossing the boundaries, then we know how much is being transported in or out of the cell. Okay. All right, any questions on this before we move on?
So you said it could enter or leave because of convection?
Yeah, it can leave the cell due to convection. So you can think about it like you have just a region in space, right? Just like this. Okay. And remember, convection represents a velocity. So let's say that the velocity is kind of going through just like that. Okay. So if we have phi that's out here, right? So the phi can enter the cell through the convection velocities, but then the convection velocities also can take it out of the cell as well. Right? Okay. Any more questions? Okay. So let me go clear this. Okay, so let's talk about how do we actually evaluate those line integrals. Because right now those have been kind of like a little bit of a nebulous thing, right? So let me draw our cell, which is going to be just a square. Okay? And then what I'm going to do is that each side of the cell, I'm going to give it a different number, okay, for each of the different sides. So we'll call this one 1, call this one 2, 3, and then 4. Okay. So when we evaluate this line integral, so let's say that we're evaluating the diffusive line integral. So we're taking the integral of k gradient of phi dot n ds. Okay. When we evaluate this, basically what we say is we need to go all the way around the cell. Okay. So the notation I use for this is I give this little circle, which makes the integration kind of look like a music note. So what that means is we need to go a complete circle around our cell. Okay, but because our cell in this case is a square, and the square has sharp corners, it's actually going to be really hard for us to kind of go around in just one fell swoop. Okay, so what we do instead is we break up this line integral into 4 different components, or 4 different sides for each side of the cell. Okay.
So just to be clear, now we're going to include the corners?
We're not going to include the, well, no,
Or
we're not.
the corners are part of the lines?
Yeah, the corners are part of the lines, but we're gonna integrate over them. So you'll see, we're not actually going to perform the integration. We're just going to use trapezoidal rule. But we need to make sure we get basically 4 different integrals out of this guy. Okay. So if we break up this integral, okay, it's going to look like this. So first we're going to integrate over side 1, right? So this can be k d phi n hat ds. Okay. And then to this, we're going to add the one on side 2. So on side 2, we have k. And then we have the component on side 3. Okay. And then finally, we have the component on side 4. So it seems like we're making the situation more complicated because now we started with 1 integral and now we have 4 of them. Okay, so we have a question. So the question is, how would this apply for irregularly shaped regions? So that's a great question. So the say if you have like a hexagon or a pentagon, something like that. Basically, whenever you go around a sharp corner, it's really hard to kind of integrate straight on that. So you need to kind of integrate this according to 1 for each side. But if you had kind of a rounded shape, like you have a circle, you can actually go around the entire circle with one integral, just because there's no sharp corners there. But for the finite volume method, it's really rare for you to see circular cells. Oftentimes squares and rectangles and boxes are kind of the most common just because they're kind of easy to interpret. You might see triangles or tetrahedrons. In that case, you would only have to integrate over 3 sides of the triangle. Right. Yeah, good question. Okay. Any more questions?
For the integrals, you're just labeling them like subscript 1, 2, and 3. Like we're not going from like 1 to 2.
Yeah, so I'm just leaving them kind of generic for now. So we'll see. Right now we're kind of just kind of introducing the theory, but how these actually turn into algebraic equations, we'll go over that once we start doing the diffusive term. But I kind of just want to go over just the quick overview of this before we kind of jump into that.
Professor, for the even numbered integrals, are we not putting the vector notation over the gradient with phi, or is that just?
I just missed it.
Oh, okay, no worries. I was wondering.
Yeah, thank you. Yeah. Oh, I forgot for this guy too.
He favored. The odds were in his favor.
That was not intentional, but I appreciate the humor. I think through these challenging times, I think humor is something really important. So if something can make you smile on days like this, that's always a good thing. Okay, any more questions before I clear the board? Okay, so let's go ahead and clear this out. Okay. So now let's bring in the trapezoidal rule. So we've seen how the divergence theorem can help us with these integrals. So let's see how we actually use the trapezoidal rule. Right? Okay. So let's see. So the finite volume method is interesting because we go through all this trouble to set up all these integrals, but we never actually perform any integration. So up to this point, what the finite volume usually consists of is you set up all these integrals, you make it look really complicated, and then you make it look really simple with the trapezoidal rule. Okay. So let's see how we do that. Okay. So let's go back to our situation from before. So we have a cell that looks like this. Okay. And let's take one of these side integrals. So let's take the integral on side 1. Okay. So we have integral of k and ds. Okay. So normally, we would have to actually perform this integral, which is usually a big pain. But remember, the trapezoidal rule, what it allows us to do is it allows us to perform this integration without actually integrating. Okay. So by the trapezoidal rule, this is going to be equal to the integrand. So the integrand is going to be k, a gradient of phi dot n hat. Okay. And then we're going to evaluate this at the centroid. Okay, so what that means is that we're going to evaluate this at the centroid of our integration domain. Okay, so remember our integration domain is this side of the face right here. Right? Okay. So pictorially, we would evaluate it right here. Sorry, there's a crying baby outside my office right now. Hope they're okay. Okay, so that's where we'd evaluate this. And then the other part of the trapezoidal rule is that we have to multiply it by the length of our integration domain. Okay, so our integration domain here is side 1. Okay, so if we knew the length of this side right here, so we'll call the length of this side S, right, capital S. So in order to evaluate this integral, we would take that value, evaluate it at the centroid, and then we'd multiply it by S right there. Okay.
Professor, is the centroid like the center of that line?
Exactly, yes. Yeah, the centroid is the center of that line. Mm-hmm. Or the midpoint. Since we're in 1D, we can say that the midpoint of that line. Okay. Right. So if we know how to evaluate this guy at the centroid of the face, then we can actually evaluate this integral really, really easily. Okay. But there's one problem with this, because remember, when we're solving the finite volume method, we're not solving for the values at the face, right? What we're interested in actually is the values at the centers of our cell, right? Okay. So if I kind of just draw kind of a kind of representative case, right? So let's say that we have a 2-cell system like this, right? So according to the cell-centered FBM, we're interested in the values right here. Okay. So these are what we're going to be solving for. Okay, because that's what we want. But to evaluate this integral, we don't need, or we don't want these actual self-centered values. What we want is the value at the centroid of the face. Okay, so we need actually this guy. Okay. Okay. All right, so how do we rectify this? So we'll, I actually had planned these lecture notes to kind of, for this to be the end of one set of lecture notes. So, this would be the point where I'd say, stay tuned for the next episode of Dragon Ball Z. But, the next episode of Dragon Ball Z is going to be happening right now. Okay. Okay, so that's kind of it for the introduction to finite volumes. So, are there any questions before we move on to diffusion?
Wait, real quick, what's your favorite Dragon Ball Z character? Since you brought it up.
Gotta be Goku.
Goku. Yeah, it has to be Team Gohan, like during the Cell Saga.
Yeah, yeah.
We never got the Gohan that we wanted.
All right, any final questions on intro to FEM? Okay, so let's go ahead and clear this out. Oh, my clear button is, there we go. Okay, so now we're going to move on to diffusion. Okay, so what we just went over was kind of just the general overview of finite volume, the method. So we looked at both the diffusion and convection term there, but kind of just like we did for finite differences, the way we're actually going to build up this method is we're going to go one term at a time. Okay, so the first thing we're going to do is diffusion. So just like we did with finite differences. Okay, so we're going to start with diffusion with Fe. Okay, so if we look at the, if we eliminate the convection term and we eliminate the unsteady term for our general conservation equation, and we put it in vector form, it would look something like this. Okay. Okay. So thankfully, it's a much shorter of an equation, so it's easier for me to write with this stylus. Okay. So we have minus the divergence of k times the gradient of phi is equal to Q our source term. All right. So oftentimes what we do in this class is we assume that K is a constant. So we can pull it out of this guy. Okay. So the equation that we're going to be working with is going to be minus K.
Is that a
times the
negative
divergence.
volume, or
Wait, say again?
the formula, is that negative volume, or?
No, it's a nabla operator. So this is the nabla right here. So that's kind of like the operator that lets us do kind of partial derivatives. Okay. Okay, so remember where this guy, the combination of nabla and this dot product, this is the divergence. Okay. So we saw how we did how we dealt with that last time. So when we take the integral of this, which is what we're going to do for the finite volume method, this is going to turn, or we're able to transform this into a surface integral, or a line integral, sorry, using the divergence theorem. Okay. Okay. So at this point, I just want to remind you guys that it's the goal for finite volumes is the same as finite differences. Is we're going to take this equation, where this equation here is a differential equation, and we want to turn it into an algebraic equation. Okay. So the way that we do that is going to be different. Obviously, for this one, it's going to be very different from finite differences, but the end goal is going to be the same. Okay? But the kind of the amazing thing with diffusion, and actually with convection too, is that even though we're going to go about it in a very different way, what you'll see is that the algebraic equation that we get is going to look very, very similar to our finite difference. Okay? And the reason for that is, we're simulating basically the same physical phenomenon. So it makes sense that, no matter what method that we use, we should get the same answer, essentially, right? Because our mesh doesn't look any different. Our mesh is still going to be a grid of some kind. It's just that we're kind of shifting our focus away from the grid points itself to the regions. Okay. So the biggest difference here between the finite difference method and the finite volumes is going to be in how we do the boundary conditions. Okay. So we probably will get to that probably at the end of today. Whereas, in the finite differences, what we saw is that when we applied the boundary conditions became equations themselves. Right? Right. So in FDM, which is finite differences, boundary equation or boundary conditions became equations. But in FVM, what's going to happen is that when we apply our boundary conditions, what they're going to do is they're going to modify our existing equations. So it's a slight difference. So, some people might like the finite difference method where, it becomes just really clear what the boundary conditions are. But some people, especially from a coding perspective, FVM ends up being a little bit more compact just because you apply the same equation to kind of basically every cell. It's just you perform just some slight modifications for the boundary conditions. Okay. So it's a matter of preference for this class. So that's why for the final project, I'm letting you choose between either the finite difference method or the finite volume method. Either one's going to work great for your final project. Okay? Unless you're a grad student. If you're a grad student, you have to do both. Okay, any questions on this before I wipe the board? Okay. Okay. So before we move on, let's kind of remind ourselves what diffusion represents. So physically, what diffusion represents is the passive transport of some material equally in all directions. So say that we, if we take our air freshener example, so say that we squirted a little bit of air freshener into the air, and first it occupies a space like this. Then eventually by diffusion, this this little cloud of air freshener is going to spread equally in all directions, and then kind of become a much bigger cloud of air pressure like that. Okay? So the key here is that to get from the first way to the first picture to the second picture, our little jelly bean kind of just spread out kind of evenly in all directions, just like that. Okay. So let's talk about just really quickly just some practical engineering applications. So where you would see diffusion, because I think at this point in the class, we've been talking about these equations just just generally through their mathematics, but I think it's important to to relate these to physical situations. Okay. So if you find yourself working in situations that have these, then you can use kind of the codes that we wrote in this class to simulate their behavior. Okay? So kind of going along with the air freshener. So one thing that's often of interest, especially for environmentalists, is to calculate how a pollutant or some concentration goes throughout some fluid. Okay? So let's take a leak. Okay? So let's say that we can model the spatial distribution of pollutant. Oh. So that's one thing. Okay. Another thing that you can model is the temperature distribution in a sheet of metal. Okay. Because temperature is something that can be transported with this equation, so we can definitely model that. Okay. And maybe one that's relevant to maybe something you see every day, where you got a cup of coffee from Starbucks or something. Maybe not now because Starbucks is closed, and then you pour some milk in there. Okay. So the milk, if you just let it sit there and you don't stir it, then the milk's going to passively spread throughout the coffee. So all of those things can be represented by diffusion. Okay. Any questions on this before I wipe the board? Okay. Okay. So mathematically, as we've seen, diffusion is represented by a second-order derivative. And the way that we, if you kind of remember, the way that we modeled this with finite differences is we used a central difference scheme. Okay, so if we take d squared phi dx squared, okay, what we said was that this is equal to phi at I plus 1 minus 2 phi I plus phi I minus 1 all over delta x squared. Okay. Where kind of the key observation here is we had kind of equal weights on the left and the right. I remember when we went through the convection, we said that this makes a lot of sense because since diffusion doesn't have any preferred direction, things are just going to spread equally in all different directions. It makes sense that our finite difference kind of reflects this. And yes, this is assuming a central differencing scheme. So for second derivatives, we mostly just use a central difference, mostly because diffusion it has things spread in every single direction. Okay. So that's just a very quick review on the finite difference side. So now let's do it with finite volumes. Okay. So just like we did with finite differences, let's start with the one-dimensional case. So let's do 1D diffusion with FVM. Okay, so let's write out the equation. So our one-dimensional equation will look something like this. Okay. So I'm going to write it in a little bit of a strange form, but remember we're going to be integrating this, so this is actually going to help us with the integration quite a bit. Okay. I forgot the K. Let's see. Okay. So our 1D diffusion equation is going to be minus K, which is our diffusion coefficient, times d dx, which is our spatial derivative, times d phi dx, is equal to q of x. Okay. So if you notice, if you combine this term, you'll get our second order derivative. But I've separated the derivatives just so when we integrate, it becomes a little bit easier. Okay. Okay. So when we apply the finite volume method to this, we're going to integrate this. Okay. And the region which we're going to integrate, because remember we're in one dimension, so our one-dimensional cell is just going to be a line. Okay. Okay. So we're going to integrate it over this region right here. Okay. So just for notation's sake, I'm going to call the left node, we'll call this XL, L for left, and then we'll call the right node XR. Okay. So we're going to integrate our equation here from XL to XR, right? So if we do that, we get the following. So we get minus K times integral from XL to XR of D, oops, d dx of d phi dx is equal to q of x. Okay. And so remember, at this point, what we do is we take this integral right here, or we integrate this. Source term doesn't get to escape, right? Okay. At this point, we usually take this integral here and we apply the divergence theorem. Okay. But if you remember from Monday's lectures, that when we apply divergence theorem in 1D, that's called just integrating the thing. Okay. So when we apply the divergence theorem here, this dx is going to cancel out with this dx. Okay. And then all we're end up with is integrating the d of that guy. Okay. All right. Any questions before I clear this board?
Why wouldn't the dx cancel with the d phi dx?
It can do that too. So you can cancel it with this guy. But the point is that you still have one dx left, and the integration dx is just going to cancel out one of them.
Oh, I knew that.
Mm-hmm. Okay. So I'm going to go clear the board. Okay, so let's go ahead and perform that integration. So we have minus k integral from xl to xr of d phi dx, okay, is equal to integral of q of x dx. Okay. So on the left-hand side here, we can just integrate this guy. So on the left-hand side, we have minus k times d phi dx evaluated at the right side minus d phi dx, which is a regular derivative, evaluated at the left side. Okay. And then the right-hand side, since we don't know what q is, but remember we dislike doing integrals. So whenever we have an integral that we can't do, we're just going to replace it with trapezoidal rule. Okay. So let's integrate this with trapezoidal rule. So by doing that, we get q of xc times the length of this domain. Okay. Where the length of this domain is xr minus xl. Okay. And xc is xr plus xl divided by 2. Okay. So we avoided doing an integration on the right just by using the trapezoidal rule over there. Okay.
Are you multiplying qxc times xr minus xl?
Yes, yeah, where this right here, remember this is the length of our integration domain. Because in order to do trapezoidal rule, we evaluate the integrand at the centroid, and then we multiply that by the length of our domain. Okay. So that takes care of the right-hand side. So actually, we don't have to worry about that. But now we have to worry about these guys right here. Okay. Because what these guys are saying is that we have to evaluate the derivatives at the nodal points of our cell. Okay. Okay. But remember the problem that we talked about before. So we're kind of stuck here again, where we have we have our domain here, right? Where say that we're performing the integration on this guy. Okay. So what this integral is telling us is that we have to evaluate d phi dx here and here, right? But remember, in finite volume methods, we don't want to do this. We want to avoid using the grid points if we can, right? So what we want instead is we want to evaluate things here. Or in other words, we want to put the equation in terms of our self-centered values. So actually, that was kind of a poor picture. Let me try a better one, okay? Because we need 3 different cells. Okay, so this will be cell L for left, cell C for our cell, and then the right cell. Okay. So let's say we have a 3-cell system just like this. Okay. So we have the cell C. So cell C, this is the one we are integrating over. Okay. And then we have the left neighbor of the cell and then the right neighbor. So that's given by L and R. Okay. So according to the equation above, when we perform the integral on this, right, in order to evaluate that integral, we need the values here. And then we also need d phi dx here. Okay. But we don't have that, right? So instead is we have the values at the cell centers, right? So we'll call this phi L, we'll call this phi C, and then phi R, okay? And so what we want is we want some form of the derivative at the cell vertices with respect to the cell-centered values, okay? So actually, you know, the way that we're actually going to do this is we're going to rely on an old friend, and the old friend is we're actually going to use a finite difference, right? So even though we're doing the finite volume method, we can't escape using finite differences a little bit because it really helps us out quite a bit. Okay. All right, any questions on this board before I wipe it? Okay. Okay. Because let's put our derivatives in terms of those values. So actually, let me draw that that figure again. Okay, so we have L, C, and R. Okay, with the corresponding phi L, phi C, and then phi R. Okay, and then so from our finite volume equation, what we want is we want d phi dx evaluated at xl, where xl is this guy right here. Okay. And then we also want d phi dx evaluated at xr, where xr is this guy right here. Okay. So what we can do is we can you know, approximate these with the finite difference. Okay? Because what the finite difference says, we can approximate the slope of this line using two discrete values and the spacing in between them. Okay? So d phi dx, if we use a forward difference, right, at xl, the way we can evaluate this is at say phi c minus phi l, all divided by delta x. Okay? Where we say delta x is this distance right here. Delta x is the distance in between the cell centers. Okay? And then similarly for the right side, we can say that d phi dx at xr is equal to phi r minus phi c all over delta x. So one small point before we move on, but according to just with regard to the spacing between the cell-centered faces. Okay. So if you remember from last time, what we often work with are even grids. Okay. Where even grids mean that all the cell points are the same distance apart. So for finite volumes, what that means is that all of our cells are the same length. So for even grids, delta x, which in this case we've taken to be the distance between the cell centers, delta x is also going to be the same as the length of the cell. So that kind of simplifies things a little bit for us. Okay? So let's go ahead and plug these two guys into our equation. Okay? So we get that delta minus k. The first thing was d phi dx at xr. So let's go ahead and plug this guy in right here. Okay? So we have phi r minus phi c all over delta x. Okay? And then from that, we're going to subtract d phi dx at xl, which is going to be this guy. So we have to plug that in right there. So we have phi c minus phi L all over delta X. Okay, so that's the left-hand side of the equation. And on the right-hand side, we have QC, or Q at XC, right? And then we're multiplying that by the length of our cell. So if we take the assumption from the previous line where our grid is even, we're going to multiply by delta X. Okay. All right. So you can we see that we started from integrals, but then now we're getting to the point where we can see an algebraic equation. Okay. Let me make this a little more clear because these two guys look the same. Right. Oops. Okay. So the guy on the left right here, this is phi C, and this one is phi L. Okay. Okay, so let's simplify this a little bit. So let's get all the phi terms on the left, and let's move everything else on the right. Right. So if we do that, we get the following equation. We get phi R minus 2 phi C plus phi L is equal to delta X squared all over minus K times Q at XC. Okay. And then this right here, this is our general equation for one-dimensional finite difference or finite volumes for diffusions.
Okay. Professor, can you say that again, please?
Yeah. So this equation that I boxed right here, this is our general kind of we call it the coefficient equation for finite volumes for 1D diffusion. Right. So you remember when we did finite differences for diffusions, we got a coefficient equation, right? Where we got an equation in terms of i's, where in order to get kind of our system of equations from that, we took that equation and we plugged in various values of I. So this equation is going to give us the same thing. So what we're going to do is we're going to take this kind of general equation, plug in different values for the cell indices, okay? And then from that, we're going to get our system of algebraic equation. Okay? Right. So hopefully, this equation looks very, very similar. So actually, this equation is basically identical to our finite difference coefficient equation for diffusion. So on the left-hand side, you see we have a coefficient of 1. On the right neighbor, we have a coefficient of -2 for yourself or your own MyID, and then we have a coefficient of 1 for the left neighbor. Right? And on the right-hand side, we have the grid spacing squared divided by the diffusion coefficient multiplied by the source term. Right? So it seems like we did all this work and we ended up with an equation that we already kind of knew. Right? But there's one subtle difference here. So the subtle difference here is that this source term, this is evaluated at the centroid, whereas in finite differences, this was evaluated at the grid points. But it's a minor thing, so it usually doesn't make too big of a difference in the results, right? But the fact that we got the same equation here is no mistake. So remember, we're simulating basically the same physical phenomenon. We're just using a different method. So for the case of just kind of really simple diffusion, we actually literally get the exact same equation. So that's kind of disappointing and also reassuring at the same time. Okay. All right, any questions on this before I clear the board? So there's a question right now in terms of efficiency. So are you referring to which method is better? So both methods, in this case they'll give you the same equation. Actually, the implementation, the code looks very similar too. So for these kinds of problems, it doesn't really matter which method that you end up choosing. Kind of like what we talked about on Monday, where the two methods, they have kind of very subtle differences and the properties that they have. One nice thing about the finite volume method, when we start to take convection into account, is that the finite volume method is conservative. So you know that once you put some mass or you put some quantity into your system, and you simulate it with finite volumes, all that mass is still going to be there, right? So that's actually not guaranteed in the finite differences. So in finite differences, you might have kind of small gains and losses of mass here and there, just because of how you discretize the equation. But for finite volumes, you're guaranteed that however much you start with, you're going to have the exact same amount in the end. So actually, that's something really nice for fluids. So I don't think we're going to get to solving the Navier-Stokes equations, so especially kind of with the new schedule that we have. But for fluid mechanics people, they love finite volumes, especially for that property. But in terms of efficiency, they both can solve the same equation with the same accuracy and with the same speed. Okay. Any more questions on this before I clear the board? Okay. So I have to switch to the PDF mode just because there's the camera button is kind of locked into the bottom left of the screen, so it blocks my my clear button. Okay. Okay. So just a quick note. So I know we use the finite differences to get that the value of the derivative of the phase, right? So what that implicitly assumes is that we assume that the variation between cell centers is linear. Okay? Okay. So if we draw kind of the graph, so this here we say that this is phi L. So this is the solution at the left neighbor, right? And this is phi C, right? And this line right here represents the face. Okay. So by assuming that the form that we did, we basically assume that the difference in between these two, or the variation, is linear. Okay. And then the slope of this linear line is given by the expression that we had before. Right? So this will be phi C minus phi L all divided by delta x. Okay. Right, so just a small thing. So actually, it's a small thing now, but for the project, what you're going to assume is that this variation is not linear if you choose to do finite volumes for your project. Okay. Okay. So basically, what you're going to do for this equation, so I'll probably will get into boundary conditions next time, is that we have this equation, and then say that you have your finite volume mesh, right? So you say you have this line, right? So you have a bunch of cells right here, right? So let's say we have cell 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so the way that you're going to get your algebraic equation is you're going to take the equation from the previous line and apply them to each individual cell. Okay. Not apple. So in this case, we have 8 different cells. So we're going to apply that equation 8 different times. And then from that, we'll get 8 different equations. Okay. So where we'll pick up on next Wednesday is we'll see how we deal with these guys, the cells that border the boundaries. Okay. So the treatment of the boundary conditions is a little bit different for finite volumes than it is for finite differences. Okay. Okay. So with that, we're out of time for today. So I hope everyone has a great weekend. Stay safe. Stay healthy, everyone. Right, and as soon as this lecture, I have it downloaded, I'll put it up on YouTube so you guys can view. Okay, so have a great weekend. I will see you guys next week. Okay, okay. So I'll stay on the line for a little bit for any last-minute questions, but then I'll probably, because I have another lecture at 7 o'clock, so I'll probably end the meeting in about 5-6 minutes. Okay? All right, see you later, guys. Yep, so the homework's still going to be due next Wednesday because the homework, it doesn't have anything to do with the finite volume stuff. So the homework is just using the unsteady stuff. So that's explicit Euler, implicit Euler. So we finished that stuff on Monday. So you should be good to go for the homework. All right.